All right, hello. Thank you for tuning in to this talk, the name of which is Predictions of the High Wind Drag Coefficient and Potential Underestimates Using Dropsonde Data. This is some work that I've been doing with my postdoc, Charlotte Wainwright, colleague Dan Stern at the Naval Research Laboratory in Monterey, George Bryan at NCAR, and Dan Chavas at Purdue. And so this is some stuff that we've been doing on and off for several years now. But before I get into some of that, as many of the talks, not only in this session in the Air-Sea Interaction conference, but in the entire Air-Sea Interaction conference as a whole, is trying to characterize air-sea transfer at high winds. And this is a fantastic video that I got from Dr. Byron Blomquist from the High Wings campaign in the North Atlantic. So this isn't even a hurricane. And in fact, if you notice, this isn't even yet Category 1 wind speed. Trying to characterize the transfer of heat momentum at an interface like this is really difficult. And as you can see, they're not even allowed on the deck in these kinds of situations. To try to measure how much, in their case, they were studying gas transfer, but even momentum, heat, moisture, when you've got large swell, small waves, spray being kicked up, bubbles and all of that, is very, very difficult. So a lot of our ability to characterize it is based on estimates. At the same time, if you're trying to take, something like Hurricane Maria and model it numerically, at some point you're going to have to set the boundary conditions, right? And this is where, often setting the boundary conditions for the lowest, most grid points comes down to some of these bulk transfer coefficients, right? So the total momentum is characterized by CD times some reference velocity squared. It's often defined using a 10-meter velocity, but it could be related to the wind speed at the lowest, most grid point that you have. And you've got the same for sensible and latent heat. Often you can combine these into a enthalpy flux, and the enthalpy flux coefficient is often assumed to be the same as the other two. But today I'm only going to focus on the drag coefficient because, as we'll see, this is hard enough to estimate. So who cares? What is the point, or what is the sensitivity of numerical predictions to CK or CD? Well, there's a lot, in fact, and many of you probably know this, but the famous result from the steady state theory of Kerry Emanuel, and this is from Jazz in 1995, shows that the maximum velocity in a storm actually goes like CK over CD to the 1/2. Because there's this idea that the CK over CD ratio is saying, well, how much fuel is there for the storm relative to how much drag or sort of inhibition of the strengthening of the storm. So with more CKs, or with more enthalpy flux relative to the drag of the surface, you get a stronger storm. Well, others have done, this is a steady state idea. Others have done, sort of more transient. So what does the development of a storm look like for a bunch of different values of CD? Same thing here, Green and Zhang in 2014. What does the time history of the development of a storm look like for different values of CD and CK? And the answer is that it varies quite a bit, because again, this is what ultimately controls a lot of the balance. Well, okay, then the next logical question is, can we estimate CD at high winds? Can we actually predict what some of these values are and know what to assign them in the numerical models? Well, this is kind of a famous paper done in 2003 by Powell et al. In Nature, where they were kind of the first to find that the CD actually looks like it rolls off. And so not only does it not continue to increase, but it looks like it actually starts to decrease at higher winds. I'll say much more about that as the talk goes on. These are direct measurements made from aircraft, so eddy covariance made from aircraft during the Sea Blast campaign. These are oceanside measurements. These are oceanside measurements, which also kind of hint at this roll-off of the CD versus U10. These are measurements made by Potter et al. From a buoy during the ITOP campaign. We also have a number of laboratory measurements. And the laboratory measurements, as I'll mention towards the end here, actually look like they saturate. So these are done at the Miami wind wave tank. These are an updated version of the same ones because there was an error in the post-processing of these ones. You can look at Kurtic and House. There's the Japanese wind tunnel, which shows a saturation, and the wind tunnel of Troitsky et al., which seems to suggest as much too. So there's a lot of different ways of trying to estimate CD. But as you can see, there's even some qualitative differences in what happens with the high wind behavior. So today, I'm only going to focus on the dropsonde flux profile method. So how reliable are the estimates that have derived from dropsonde profile? So as I mentioned, the first of these is Powell et al. In Nature 2003, where, again, they were the first to see this rollover of CD, and it looks like it actually starts to decrease at high winds. Well, some members of the same group had a follow-up in 2012 where they basically repeated the process, but on a slightly expanded data set, and saw much the same thing. So they didn't Holthusen at all. They see the roll off the CD, and they actually kind of broke it out into storm relative position to try to argue something about the alignment of winds and waves. And then myself and some colleagues in 2016 also used dropsondes. We were looking at the thermodynamic profiles as well, but when we did the CD, we were trying to characterize some of the uncertainty that came about when using this. And so we're sort of expanding on that a bit in this talk or in this study here. So let me say something about the flux profile method itself. It's actually quite straightforward. The first thing you do is you construct mean profiles. You take all of the dropsondes in a certain category, and the way that Powell had done it was actually categorizing based on the average boundary layer wind speed. He says, all right, I'll take all of the sondes which are in the range from 20 to 30 second, 30 to 40, and so on, and I'll average all the velocity profiles together. If you then invoke Monin-Nabokov similarity theory, you would expect to see a straight line on a semi-log plot. And the slope of that line is kappa, or that's the von Karman constant, over u star, which is related to stress. And indeed, for these cases, you actually see something that looks an awful lot like a straight line. So once you construct the mean velocity profile, you say that it's a logarithmic profile whose slope is u star over kappa. The z naught, or the intercept of that, is related to the z naught, the roughness length. Well, tau, the stress, is related directly to this measured or this estimated value of u star. Once you know tau, you also know u10 because you have the equation for the mean velocity. Now you can actually calculate what CD is, or estimate what CD is. So this is what I'm referring to when I say the flux profile method for estimating, and constructing it based on dropsondes is the way that Powell and Holthusen and myself have done in the past. Okay, so if we just simply take this method and we repeat the analysis of Powell et al., but we're just using all of the data now, dropsonde data all the way through 2018, what do we see? Well, if we look at the logarithmic profiles, or there's the velocity profiles as a function of height, what we see is that indeed, again, they look fairly logarithmic. Okay, I mean, one argument is that there is no such thing as a logarithmic layer inside hurricanes, but it certainly seems like if you average them together, you get something that looks very logarithmic. If we look at the u star as a function of u10 and the corresponding CD as a function of u10, what we see is, these are the black symbols here, they actually sit almost right on top of the Powell and Holthusen studies, which makes sense because we're using basically the exact same procedure on much the same data set. However, at the highest winds, we actually start to see a discrepancy, which is kind of the focus of the rest of the talk. The first thing we do is to say, all right, let's just go back and see if we actually take the Holthusen study and we actually only look at the dropsondes from those years. If we actually split the full data set of dropsondes into the years that they use and then the years following, this is what we see. So on the left here is the date range 1997 to 2005, which is what Holthusen had used. Then we also have sondes from 2006 to 2018. The numbers are comparable for all the different the wind speed ranges. But what we see is very interesting. If we look at CD as a function of U10, if we only look at the 97 to 2005 range, we see the black dots here tail off or roll off just like the yellow stars, the Holthusen data, which is what we'd expect, again, because we're using the same data with basically the same process. If we just simply take the new data, however, you actually see a jump in the CD, right? So you're actually seeing a qualitatively different behavior of CD. Now, this raises some interesting questions. Does this actually have to do with the date? It's worth noting that during the time, right, during these two times, here's the 97 to 2005, here's the 2005 to 2015, there were actually a number of updates to the dropsondes, right? So the GPS receiver was updated in 2005. The system was upgraded to AVAPS 2. The wind sampling was increased from 2 to 4 hertz, although this doesn't really affect what we're doing because we still use the pressure, the geopotential height is gotten from the measurement. But the sondes had actually been updated, and so perhaps this could be it. This is more or less speculation or hypothesis at this point. Probably more likely is just random error. If we take the entire set of dropsondes that we have, and we just simply subsample. We say, all right, let me just break it randomly up into thirds and calculate the CD U10 and the U star U10 relationships using these random samples. We repeat this 20 times. The green shading is telling you, or is the range of CD U10 relationships that you can get from randomly subsampling the entire data set. And so what this is saying is that you could actually get a CDU10 curve that looks like this. If you take one subset, you could see it look like this if you take a different subset. These are qualitatively different. One has this roll off that that there's much debate about. Others have, continue to increase, and others look like they plateau, much like the measurements done in laboratories. So there is reason to believe, just simply by looking at the random error associated with subsampling the data set, which came about because we took these two different date ranges, or led us, that's what led us to start investigating this. There's reason to believe that the roll-off is actually not a robust result. It happens to be that that set of data has a roll-off, but different sets of data don't. To look at this a little bit further, we turn to some numerical simulations, either CM1 LAS simulations of Stern and Bryan in 2018, where they use virtual suns. They construct virtual suns where they launch, they have 30-meter resolution, so they're resolving a lot of the turbulence, and they launch 100,000 virtual dropsondes into this. Well, here's a situation where now we know what the true value of CD and U star are because they're prescribed in the model, and we can actually repeat the exact same analysis and see if we can recover the known value. And if we do this, so here's the mean velocity from a bunch of different dropsondes, now binned by their location relative to the RMW. So, the gray curve is all the sons launched between 0 and 0.26, 25% of the RMW, and so on. The different colors continue on. Well, we fit a logarithmic region. Now, first off, this is a very small, intense storm, so that the height of maximum wind is actually lower than what you typically see, and we don't want to fit through the lowest regions because that's where the subgrid modeling is actually being used. We don't want to fit through that, so we're only fitting through 4 grid points. But nevertheless, this dashed line down here is the true value of the wind, of the CD, and this is this dashed line here is the true value of U star. If we start at the outermost RMW, we actually see that we're in the right ballpark for estimating the value of CD using the flux profile method until we get to the RMW. So this is 1.04 to 1.3. As soon as we get to the RMW and inside, we actually start under predicting the CD value pretty severely. Okay, and so this would suggest that despite there being a logarithmic profile, the balance is, the relationship between the mean velocity and the surface flux are out of balance. And this would make sense because you have an enormous change in what's governing the dynamics down there. You've got vertical advection, a lot of convection, you have strong radial pressure gradients, and so on. And despite the presence of a logarithmic region, it appears to underpredict CD. And if we actually look back at the real suns and we say, well, look, let's try to compare some of these things to true values, right? So this line here, this black line, is from Andreas et al., where they actually calculate, U star and CD using direct measurements in a number of different studies. So these are completely independent studies. What we see is that ours and Holthusen and Powell's are all sitting to the right. Well, one thing that we started to think about was the height itself of the dropsonde is pretty uncertain. Just based on the sampling frequency and the fall speed, you could be off by maybe 10 meters. And this is huge. This is 100% error near the surface. And so if we just arbitrarily say, well, let's just add 5 meters to the height of every sun. Let's say that there's a bias, there's an underprediction, a consistent underprediction of the height in the suns. Well, you actually see, that's the difference between the black and the gray. We actually shift back towards this line. And so that's kind of saying, we're sort of hypothesizing that maybe we're underpredicting the height. If we add 5 meters to the height of all the dropsondes, we actually shift more towards true values at similar wind speeds, kind of in this range here. And that small shift in the height actually increases the CD value upwards of 25%. And so even a small bias in the height, and there certainly is uncertainty in the height, can actually lead to these sorts of things. Okay, so rather than me summing this thing up, I'm actually going to turn to my 12-year-old daughter, and I think I'll let her give you the summary of all of these things. Okay, so.
Revisiting the Powell et al. Method on an expanded data set leads to different high wind behavior. Random error precludes conclusive knowledge of the U10-CD relationship. Evidence suggests that the CD is underestimated at high winds when using flux profile method. A roll-off in CD may be an artifact as laboratory experiments suggest.
All right, thank you again for tuning in.